Hey everybody, it's office hours. We'll get started right here. We might do some 201. We got 320 is going to have a new assignment coming out here in a little bit. Not today though. It's a test for 320. 474 just got their grades back. Visualization 8, people are following along with that video, so check out the Visualization 8 video. Let's see right here. Let's go to, we've done a lot of work on 201, so maybe we'll see. If anyone's here, feel free to say hey in the chat. Let's wake up Mubot. Mubot, wake up Mubot. We'll wake up Mubot. I wonder if that blanks the whole screen when I do that. There we go. We are getting 201 loaded up here in the background. And some, let me do the homework again. A lot of people, maybe we'll work straight through the homework. So let's see right here. Here's the homework. Mubot is awake. There we go, Mubot is awake. It took me so long to figure out how to make Mubot, but now that Mubot is here, we are good. Let's see, is anyone here in the chat? No one's here in the chat, so let's hop over here and let's talk about some confidence intervals for the proportion. Let's do this. So with this right here, a catalog sales company promises to deliver orders placed online within 3 days. Follow-up calls to a few randomly selected customers show that a 95% confidence interval for the proportion, the true proportion, of all orders that arrive on time is 83 plus or minus 2%. So when you see this interval right here, this interval is p hat plus or minus the margin of error. And it's important we know the interpretation. So let's see, we've got a bunch of Word documents open right now. Oh yeah, so do we still have yesterday's? We don't have, this is all from this morning. So we can go here and say, I am blank percent confident that the true blank is contain the interval blank to blank. I am blank percent confident that the true blank is contained in the interval blank to blank. So I am blank percent confident that the true blank is contained in the interval blank to blank. Now what goes right here is the parameter of interest. So it's important we know how to interpret these intervals. This is your confidence level. This is parameter of interest. This is the lower bound. And this is the upper bound. So this is what we do when we interpret the interval. We say I am, and then we give our confidence level, blank percent confident, that the true, and then we have to talk about what we're trying to measure, that we're trying to figure out what this is contained in the interval, and then we give the lower bound and the upper bound. So when we look at the answers right here, where did our answers go? So one can be, that sounds about like I am. One can be 95% confident. Are we trying to estimate, hey, what's up, Dan? You got it, Throwback Thursdays. Is Crash on here for Throwback Thursdays? Crash is not on this screen. Or is it down lower? Daily event. There we go. I think he's on here for the Throwback Thursdays. Is that not connected to the daily event anymore? You got it. There's a, why is that not clicking on the button? Well, that's weird. I will reset up that button afterwards. Like, why is my button broken right there? So we have here I am, and then we have to think which of these sounds right. Are we trying to estimate the true population percentage, proportion, either way? Or are we trying to estimate for the sample? Well, the thing is, as mentioned earlier, this 83 plus or minus 2%, that's actually, no, the 83 plus or minus 2% is actually the sample proportion plus or minus the margin of error. So the margin of error is 2%. Yeah, we can do, you got it, philanthropic organization, you bet. So we have here the sample proportion. And what do we use the sample proportion to estimate? From the sample proportion, we're trying to estimate for the population. So this is actually a population parameter up here. And we're using the sample to estimate it. So we took a sample to estimate what's the truth for the population. So the answer is going to be the population parameter one. I keep on closing down this over here, so I can't switch between them. So it should be this. Let's give a check, and it is. Let's do the philanthropic organization. Sales catalog. Is it on the quiz? It might only be on the quiz. Ah, we found it. A philanthropic organization sent mailing labels and greeting cards to 100,000 random, there's your condition one, random, you know what's going to happen. This still works. Random donors. So we have 100,000 random donors. And they received back 5,421 with donations. So now we have to identify, you bet, Dan, you got that right. 100%, Dan. That is exactly what that interval would be. Great job. Really good practice, everybody. The more you practice, the better you get at it, and the better you can understand the intervals and how they work. Great, great work, everybody. We have to identify notation for this. So what notation do you see in this question right now? What notation do you see? And I think it said build a what % confidence roll. And I'll get that going while people try to identify the notation. I'll get the cheat sheet going for how we can get the confidence levels. I'll show it over here. So you should have, I've got this ready to go. So the notation we have, nice job, Dan, right there. Excellent work, Dan. 100,000 is N. That's the sample size. And then X is going to be the amount of successes. And then X over N, which is the amount of successes over the amount of sample, is equal to P hat. So we can find P hat right here. P hat is going to be X over N, which it's just 5,000 over 100,000, or 5,421 over, and there we go. So 5.421%. You're just doing a little bit of moving of decimals right here. Now Q hat is going to equal to 1 minus P hat. So they're complements. So all we do is we just take and we go here. We do 1 minus and 94579. So it's equal to 94579. So that is Q hat. It's just 1 minus P hat. They're complements of each other. And from here, we just need to know the % confidence. And I didn't see it. It is a 95, classic 95. So you go to the David M. Lane website. Let's just drop it here in the chat. So the David M. Lane website is where we will head off to, Mr. David M. Lane's website. And on it, we will go here and do value from an area, go between and enter in 95. So these are the values for the 95% confidence roll. It's just the plus or minus z-score right here, which is 1.96. So 1.96 is going to be the z-score we're going to use for this interval. So because it's a 95, so with 95% confidence, there's the 5, we are going to use z equals to 1.96. And that's basically 2. Basically, but make sure to use 1.96. So there could be an issue if you don't use 1.96. 1.96 is the exact. From here, we just need to start doing the calculations. We have all the notation we need. So we need the equation of P hat plus or minus the z-score. We put a star on it, meaning you pick it, but it's going to be relative to that 95% confidence. And there we go. Here's the equation, and we plug in the numbers. So to plug in the numbers, you know what I might do? We'll do it this way. P hat is 0.5421 plus or minus 1.96 square root. It's got to be a big one. 0. There's a 0 there. It's a 0. One error is all it takes in mathematics to have everything go haywire. So you always double check what you write down. There we go right there. There is the equation, and I'll show you how I solve it. Whenever I solve these, I always start by solving, and I'll highlight it. I always multiply this, then I divide, then I square root, then I multiply here. Yeah, and we do decision trees next. You got it. So we'll go right here. You're here. You ask the questions. You get the answers. So 4,579. We divide by, and then we multiply by this. What did Brian just find? What did I just find right now? No, did I not square root it? I think I didn't square root it, everybody. I was thinking about what I was going to. Someone said yesterday, they're like, you're doing this like, and it's just like second nature. And then I forget to square root something. So yeah, I did forget to square root. It looked too small. I found the margin of error. Nice job, Charlie. That is the margin of error. So if you watch the steps when I did second time properly, I found the margin of error. We all make mistakes, so be very careful. 0.0014, and that should be enough decimals. So plus or minus 0.0014, and this is 0.05421, and that should be the answer. We should have the answer right now. Let's do it. So we have 5421 and 1.4%. I think it only rounds to one decimal. So here's our margin of error. And let's copy it. Let's add 554, 2 decimals. So we should be good on this. And then I'm taking 0.054. Oh, wait, what am I doing? I'm sorry, everybody. 0.05421 plus the margin of error. 0.56. Oof, might not have given it to me there. I'm taking this right here, which is 0.05421. That's p hat minus the margin of error. If you're wondering and you just want to see it more visually, 5.28. What I'm doing right here is I'm solving the mathematical equation down here. So the mathematical equation I have at the bottom of the screen, I'm just adding and subtracting these numbers, and we show all the mathematics following down and how to solve it to right there so that we can solve for the confidence interval. It then asks if 5.4 is believable. 5.4 is in the interval. So since 5.4 is in the interval, I believe it, because I'm saying I think the true proportion of people who will donate, or rather, I am 95. Yeah, great job, Claire. I am 95% confident that the true proportion of people who will donate to this campaign is contained in the interval 5.28 to 5.56%. If it was a written test, I would make sure everyone would be saying it in class. I'd be like, you need to say it, and you need to say it, and you need to say it. So I am 95% confident the true proportion of people who will donate to this campaign is contained in the interval 5.28 to 5.56. And that's an interval we created from our sample right there. Look, when I reach right there, it's like I'm reaching through the thing and I'm going off screen. So that has it. That is that question. And these are all pretty similar on the homework. They don't have a lot of solve for n, so a little bit easier. This one's a fun one. Might come back and do this one here soon. Let's talk about on the quiz. The answer to the second part for me was no. Was it outside the interval? It'll be no if it's not contained in the interval. So if this were to ask 5.1, then the answer would be no. Does that make sense, Dan? Because the values within this interval are values we'd believe, because I think this is what I think the true proportion might be contained between. So if it gives us an interval, a value right here that's outside the interval, we would say, I don't think that's really a possible value. So if this is in the interval, we'd think it's a possible value, yes. If it's like 5.1 and it's outside the interval, oh yeah, good. No, Dan, thank you for mentioning that. Because sometimes the problem is I like helping with these videos, but then sometimes I don't explain the concept and I just click yes. And then I think people will watch the video and they'll be like, oh, we click yes right here, but then why is it yes? And so Dan really points to sometimes it can be no, because if the value is outside the interval, then we wouldn't believe it's a possible value of the true proportion. We'd say, I don't believe that's really plausible, because our interval would contradict it. So great comments there, Dan. I'm really proud of everybody. I want to hear how people do on the test. I know some people watch from other classes. So if you are watching the videos and they're helping you, tell me what helps you, and let's do a speed run of decision trees. Class is not over. Just putting up the class is over sign. I'm doing pretty well. It's, doing a lot better these weeks. Feeling a lot better. Like almost at 100%. Hoping to get to 100% soon here. It'd be really great to be back to 100%. And then just try to stay at 100%. Drink more water. Eat more vegetables. I've been making really good stir fry. Good rice, good vegetables, stuff like that. A lot less meat in my diet. Probably need to. I like soy. Soy's like, if you make some good soy, I don't know, maybe we were frying it, so maybe that was a bad idea. I don't know. I was frying it. It was my idea. My ideas are probably the bad ideas. So going to make a decision tree right here, we are going to go to partition models. Staying 100% all the time isn't. Yeah, Charlie, that is some sage advice right there, Charlie. That is some good advice. It's you can't expect to stay at 100%. You need those times where you acknowledge that you're not at 100% and then make efforts to bring yourself back, and not trying to the need to work at 100% or to stay at 100% can sometimes cause you to be way lower than 100%. So Charlie, wise beyond your years right there. And so we have right here, we're going to make a decision tree. What kind of variables can a decision tree take? Everything but what? So when I do this, the decision tree should take what? A decision tree should take what? A decision tree should take what? Seeing if there's any variables we need to remove. Identifiers are things that act like them. Yep, perfect. Those are the things we shouldn't put in a decision tree. A decision tree can predict a categorical Y or a categorical X. It can predict a categorical Y or predict a quantitative Y. It can use categorical X's or quantitative X's. And so everything here looks good to me. I don't see, if you want to look for identifiers, you got to go over here and you need to do this. I'm not seeing, we don't have original row number. BS20 is the take-home open notebook. So Ryan, the test is you get a cheat sheet. There is class today. You don't need to show you should show your cheat sheet in your room inspection, but the cheat sheet, so the test is cheat sheet. You get cheat sheet, And then the take home, you can do whatever. Like you're talking about the take home, right? So the take home is, you have access to anything. Just don't talk to friends. Don't talk to friends, and I really can't help for it. So the respondus test is one sheet of notes. The respondus test is one sheet of notes. And Charlie's, so does that make sense, Ryan, right there? The take home that you do as a take home test is you can do whatever you want. You can stuff up, just don't cheat others. Yeah, you can use other resources. Resources are fine. Exactly. Don't post on message boards. We've had people do that in the past who post their questions. They're like, hey, I'm trying to figure this out. Can anyone help me? And then two were like, are you posting this for our class? This kind of looks like a take home question. And so Charlie's 100% right here that we'd see questions that have like a whole lot of levels. We'd see questions that have just tons and tons of levels, like favorite ice cream flavor, your major, favorite color, etc. You're welcome, Ryan. Thank you for coming by and asking. I appreciate it. I want everyone to know exactly what's going on. And we have no identifiers or things that act like identifiers. Identifiers are unique for each and every observation. Things that act like identifiers have a whole bunch of levels and are kind of pseudo identifiers. So what should we predict? What number variable should we predict? We can predict any of them. What number variable do you want to predict? I will let you pick. We did the use marijuana is for the recent thing. So we could actually do that one. We could see if people use marijuana. And the number one predictor of people use marijuana, according to Stacey, said, how to spend $10,000. And then, well, remember, we're not going to take just, because we're going to use all the variables to predict this. So when you make a decision tree, you let the tree decide for itself. Like, does that make sense? You're going to look at one Y variable, like have people use marijuana. And then, so you use one Y variable and then all the X's, just so you can see. Yeah, so the point is that the tree, so you can see here, I'll relaunch the analysis. So the tree is going to pick for us what X's to use. Basically, the tree has access to all these. When I let it split the tree, it's going to look through all of these and find the best one algorithmically. We talk more in 320 how algorithmically it works with reduction of sums of squared error or Gini coefficient with misclassification rates. Don't worry, we won't go into that here. But it'll look through all of these variables and be like, what is the best variable and where's the best place to split it? Yes, and then the first split is the most kind of important split that does usually the most variation explained, and it's how much people drink. So what's really interesting, at least about this tree, not like super interesting, but are these people right in here? Can you tell me about these people up here? Tell me which are these people here. You see how this is leaf 1, this is leaf 2, this is leaf 1 right here, this is leaf 2, and you see this blue area right here is this blue area? What can you tell me about these people right here? These people right here, what? Tell me about their X characteristic. It says Q37, night, month, drink, less than 1. So what do you think basically describes these people? These are people who do what? Their nights a month that they drink are less than 1. So, well, they are, these people as a whole are less likely to use marijuana. Have these people up here used marijuana? Have these people right here? So as a whole, that group is less likely to use marijuana. That is true. And these people right here, well, wait a minute. Look at this variable right here on the other side here. I'll make it a mosaic plot really big. So do you see how these are the, yeah, exactly. So these people up here have used marijuana. And then how much do they drink? How much do they drink? Where's my, there we go, that one. How much do those people drink? So these people here have used marijuana. If you look on the Y scale, they have used marijuana. And then the amount they drink, less than 1 drink a month, which basically means they don't drink. So these are people who don't drink but have smoked marijuana. Maybe it's a life choice now, but they have smoked marijuana and they don't drink. And these people over here drink at least some, and you can see a greater proportion of them are using marijuana. So these are people who drink at least one night a month. And then these are people who have smoked marijuana. And these are people who have not smoked marijuana but drink more than 1 drink a month, 1 or more drinks a month. The next variable right here is going to be ever driven drunk. Not a good choice. Don't drive drunk. And so these are the people here who drink at least 1 drink a month and have driven drunk. And that first split is what explains the variance. Yeah, it's going to be the first split usually does the most amount of variation explained. If you notice how the R squared jumps to 17, then goes to 25, and then goes to 27, it kind of gets less and less and less. And driven drunk is also over here. But if you look, the people right here who are least likely to have ever used marijuana are the people who do not drink because they drink less than one drink a month, and they've never driven drunk. So these people are super likely to not have used marijuana. Oh no, what do you want me to repeat again? Let me try to repeat. So when you look at it, I'll try to explain a different way. Let me see, because I don't know exactly what I said. When you look at all of these leaves, leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, all of these leaves, they correspond down here to leaf 1, leaf 2, leaf 3, leaf 4, leaf 5. And what you're noticing right here is the distribution of the Y variable. The blue means people who have smoked marijuana. The red means people who have not. So this group right here is the least or the most likely to have smoked marijuana. This group over here is the least likely to have smoked marijuana. We can make another group over here if we want, and it'll now be leaf 1 down here. So fun topics. People, wow, is it every single person? No, there's one person. Wow, that's insanity. So there's one person right there, one individual, which is so hard to see. I think they are barely right there. We can look at the leaf report. But these are people who drink at least one night a month, have driven drunk, and they use cocaine. I hope no one else is lagging. It's not showing we're dropping frames. But try reloading the page. Yeah, might just be internet. Hopefully internet's fine on my end. Let me look at the statistics on this. Your stream quality is good. We look to be good. 0 dropped frames. We're 30 frames per second. 5K up. I'm glad. So I think double check your internets. Move around the house if you're on Wi-Fi. But this is the distribution of the Y variable. That might have been what you heard me saying. This is the Y variable right here, which shows the people who said yes to the question for the Y variable, which is use marijuana. So you're looking down here at group 1, group 2, group 3, group 4, group 5, group 6. And then we can go to the leaf report and also display it. So when we look at the leaf report, we now see leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, leaf 6, leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, leaf 6. There's the one person we were talking about. The one person we were talking about is right there, that one red dot that has not used marijuana. So you see their answer to the Y question was no. This is the Y variable. And these are all of the X's. So these are the questions that they would say they drink greater than or equal to 1 drink a month. They have driven drunk, and they have used cocaine. And so this person, 1 out of the 70 people, has not used marijuana. And then you go over to here, this group, where these people drink less than 1 drink a month, and they have not driven drunk, and their height is greater than or equal to 70 inches. So these people are greater than or equal to 70. That's so weird that it splits on that. Greater than or equal to 70 inches, and they are super not likely to have used marijuana. Because 65 out of the 66 people, you can see the 66 right here. So the 66 are these 65 and 1 people right there. Is this making more sense, Charlie? Do you understand how to read the leaf report, which shows you the terminal leaves down here at the end? Leaf 1, leaf 2. You think it's awesome? Is this making sense? Leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, leaf 6. And you have these 66 people right here with the 66 people here. And there's 65 people who have not used marijuana. And there's 1 person who has. The 95 people right here. You have 81 people who have not used marijuana and 14 people who have. If you were to put these 2 leaves together, the 95 and the 66, how many people have used marijuana in this leaf? In this leaf right here, Charlie, how many people have used marijuana? Invariance is best described by the first. It explains the most variation usually. Yes, Charlie, if you're wondering about that, it explains usually the most variation. How many people have used marijuana in this leaf? In this leaf right here, how many people have used marijuana? And one of the best things to do, I'm going to draw this out. I should always draw out what I see in my head. So one of the best things to do is to go, wait, careful. That's how many people there are on that leaf. That is how many people. Good job, Charlie, right there. That's how many people. So this is right here, leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, leaf 6. So we want to know how many people have used marijuana in this leaf. So the people who've used marijuana in that leaf would be the people right here. So how many people are there right there? In that little blue square, how many people are there? So take a moment, see, this is a tougher test question. A lot of people get wrong. So that shaded leaf is made up of leaf what and what? That shaded leaf is actually the added together of what two leaves? That shaded leaf right there is actually what two leaves? Go down to the bottom scroll wheel and go to the quality. You should be able to increase the quality on it. I can also zoom in. But you'll actually need the bottom output for this answer. So do you see leaf 5 and leaf 6? Down here, this is leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, leaf 6. There should be a scroll wheel at the bottom that does the quality. Sometimes when the stream reloads or something, you can get to lower quality. But if you bring it up the quality, it should look better. So do you see how this right here is leaf 5 and leaf 6 would go into this leaf? So we want to know how many people have used marijuana. And so leaf 5 and leaf 6, awesome. So how many people in this top leaf up in the leaf we have shaded with the yellow, how many people have used marijuana in that leaf? How many people have used marijuana in the top leaf? It's a decent test question. How many people have used marijuana in that top leaf? For the thing I have right up there, I'll put a box up here. 15 exactly, 15. Nice job. There'd be 15 people right here. And the way we're getting that is we're adding up these two right here, because that's the addition of this one and that little tiny one right there. And then they would go back into this right here, because that's it. It's kind of like they're averaging together by their weights, because it's everyone put back together. Does that make sense, Charlie, on how to do that? It's 15. You are correct with 15, because there's one person in leaf 6, and there's 14 people in leaf 5, and that they were to join back together into that leaf, because it sections it off. The 161 people here are split into 95 and 66. Is that making sense? Like, you would see here, like, where would these go back into? You'd add 239, 322, and 8 back into each other. So you're going to add these back up. Like 70 plus 169 is 239 if you add these two back up. Does that make sense that the leaves go back in as they connect back up? So the people would go back together. These 14 and 1 would go back into the 161. So is this making sense here, Charlie? Hopefully. We'll go back and look at the decision tree. Awesome. So you can see right here, 8 plus 161 is 169. So you could figure out how many people did marijuana in this leaf. This is not a leaf, but it's out of 169. You'd have to look at leaf 4, 5, and 6. So 4, 5, and 6 is 21. Yeah, there's only so many questions, and then understanding this output's the key, because so should get 21, right? Prune below, and there's 21. So I got that by adding up the numbers. If you're wondering how I knew that was 21 before it showed, I knew that the leaves that went back into that were these following leaves right here. And then the reason I knew it was 21 was because these were the people who would go back into it. So I added those up, and there would be 21 people in this new leaf. So now this is a terminal leaf, and we get the data on it. By pruning everything below it, we now get this in the leaf report, and there's 21 people out of the 169. Of course, we can go back and show it again how it's splitting apart, and then I think we split right here, and now you notice it just has the 21 broken apart. These people get broken down into other groups. So that's a really good review of decision trees. We have the split history, which shows the increase of R squared. And if you notice, the R squared is kind of leveling off. So if you look at what's happening right here, we'd probably only go to about 2 splits. It goes up and it levels off at about 25%. We're not seeing much of an increase. This is where I've made alternate trees. I think it just needs a slight refresher. Yeah, exactly. Yeah, once you get a slight refresher, you're like, I got this. I can do this. You see, here's our 2 split tree. And with our 2 split tree, we have a tree that looks pretty decent. Explains around 25% of the variation. So 27.3%. This is a 3 split tree. The 2 split tree does 25.5% of the variation and does pretty well. 25.5% of the variation in whether or not people have smoked marijuana is explained by the variation in the tree. So overall, this model looks to do pretty well and explains a good bit of the variation. So, yep, and here's the R squared as it goes up. So the split history shows the increase in R squared after each split. R squared is the percent of variation in Y explained by the variation in X. So you can see as we make more splits, we explain more variation. And as it starts to level off, we stop splitting, because if we split, we'll always increase the R squared. So of course, with all these things, it's just going to keep dropping the menu down, isn't it? Let me close the split history. This is what's called a bad idea right here, but we're going to do it. This is a bad idea. There we go. So if you notice, the R squared is continuously going up, but this is a bad idea. This is what we'd call an overfit model. 474 was just talking about that today. This is a horrible idea. Don't do this. So that's a tree right there. That's what we got. And then we go to, let's go to split history. And the split history should show us, there it is, split history. And here's the increase in R squared. Yeah, this is, you notice the first initial jump, and they're just kind of getting some random chance variation. I wouldn't, this is craziness. There's ways to figure out in statistics if this is a good idea. I'm shocked it kept going up like it did, but it's probably just because we have a lot of variables. But overall, your initial jump in variation is here at the start. You're only at, but you're at 57%, or no, it's more like 63%, right? 64%. 64.6. And when you were at 2 variables, you had 25%. So to be almost at 60 variables, yeah, it's pretty bad. If you had a huge number of variables, could R squared? Yeah, we might be able to get it nearly that high. And this is what we call overfitting. Okay, it's not doing it. Oh, look. We ran out. So we only got to 70.8% of the variation. And it just depends on the structure of the data and everything. And so now it won't let us split anymore. We reached the minimum size of each leaf that it can be. So, and we got a lot of things classified properly, but there's a minimum size for each leaf. And I think it looks to be around 8 or 6, or 5. Wow, it can do a 5 leaf, but surely not smaller than that. 5 looks to be the minimum size for each leaf. It won't split smaller than 5 just because it's not going to put them in individual leaves. So the individuals. So this is a ridiculous tree. This is a bad idea. Don't do this. I wish I could just have a button that said bad idea. And so maybe I need to make that so that I can just have a button I press and it just says bad idea and like fire appears on the screen. So I need to make that. So let's go back. We can do, what other questions are there? Ask a question. Let me know. That's a decent review of decision trees right there, like a 20-minute review of the topic on how to talk about decision trees and what decision trees do. Decision trees can predict a quantitative Y or a categorical Y. They use quantitative or categorical X's, multiple X's, and they're awesome. They do a lot. They're super powerful. We like decision trees. Oof sound effect. I had everything in here yesterday, and I forgot to save it. So now I don't have my oof sound effect. I had it yesterday. Need to go and get the oof sound effect back in here. It's a bummer. This one right here catches a lot of people off guard because with this question, it's asking about how to interpret a confidence interval, but it gives you a bunch of bad interpretations. So what you want to do is you want to take this 73% plus or minus 1% and do the correct interpretation, where we say I am blank percent confident that the true blank is contained in the interval blank to blank. So I'm sorry, Charlie. So I am 95% confident that the true proportion of orders, no, I spelled it wrong. Orders that arrive on time is contained in the interval, and then we just give the interval, and it helps us out there. And what's it? 90? It was 95. 72 to 74%. How did I know this? Because it said plus or minus 1%. I am 95% confident that the true proportion of orders that arrive on time is contained in the interval 72 to 74%. We're going to take this interpretation right here and use it to help us out. So let's get the interpretation nice and perfect on the screen right here. There it is. There's our interpretation. And now let's take a look. This one says between 72 to 74% of orders arrive on time. This one right here doesn't even mention confidence at all. So it implies certainty. It's saying this is the amount of orders that will arrive on time. We don't say anything about the confidence, so that is definitely wrong. The next one, 95% of all random sample customers will show what? 95% of all random sample customers will show. So if we took a random sample, 95% of those random samples would show 73%. It doesn't even mention the interval, and we're not doing it for the sample customers, so this one's really wrong. So I doubt that all the samples would show that. I don't think none of the samples would show that. Probably less than 95% of the intervals made from sample, or less than 95% of sample customers would show that. That's such a weird one. That's like the weirdest one to explain why it's wrong, at least with their answers. I don't like their answers on that one. So 95% of all random samples of customers will show. It's talking about the random sample again. I am 95% confident the true proportion of orders that arrive on time. So this is talking about the random sample again. So it's about the true proportion, not the random sample. One can be 95% sure. Ooh, this sounds good to start. Oh, man, look at that. It did so well. It shouldn't be by the sample customers. It's by all customers. So I am, but notice the error right here. It gives the interval. And that's because it just explained the random sample. And so with the random sample, we know what percent of time did the random sample get their orders on time. So from the random sample, what percent of time did the random sample get their order on time? Oh, good. Look at this. This is so perfect what we have here. The random sample got their order on time. What percent of the time? So if you take another random sample, yeah, exactly. If you take another random sample, it could be a different amount. So it doesn't estimate what's true for the random sample because random samples will be random samples. This random sample was 73%. And we're not trying to estimate what will happen in a random sample. We're using the random sample to estimate the truth. So this one right here being 73% is showing us, 73% of the random sample customers got their order on time. So we know that 73% of the random sample customers got their order on time. We're using that to build an interval to estimate the true proportion of customers that got their order on time. Does that make sense, Charlie? This is actually, with this being p hat right here, this right here is the sample proportion, which is the proportion of customers in their sample that got their order on time. Does that make sense? That this is this is what the sample got. 73% of the sample customers got their order on time. When we make an interval to estimate the truth from this, we'd have this margin of error for the truth. This is from the sample. This is the margin of error when we estimate for the truth of what P would be. So this interval right here is estimating P using P hat. And so just kind of important to see the notation right here and to see when we use it to interpret. So if you took another sample and it was 65%, would it be like, I am 95% confident the true portion of blank can be... So if you had a totally different random sample and like, let's say someone said, I think that random sample you took was biased. We need to take a better random sample. And you went out and redid the research. You would have then 65 would be the center of the interval. So it would be something like 62 to 68% because it could be 65 plus or minus 3%. So if you were to have 65 plus or minus 3%, which theoretically could happen. Does that make sense? So technically the confidence interval can change based on the exactly. The random sample, and so different random samples will lead to different confidence intervals. Different random samples will have different centers to them, but 95% of 95% confidence intervals are expected to contain the truth. That's a lot of theory right there. So whenever you make a 95% confidence interval, 95% of 95% confidence intervals are expected to contain the truth. It's just to say basically the truth is in our interval 95% of the time. Not that one interval has a 95% chance, that if you repeatedly make intervals, 95% of 95% confidence intervals are expected to contain the truth. And so this one right here is talking about the sample again. We know 73% of the sample customers got their order on time. On 95% of days, what? So 95% of days, that's not what we're talking about here. So how do you represent the true proportion then? How would you take a lot of samples then average them? So you generally, like if this is actual, like let's say we're actually doing this, we're actually trying to figure out for our company. If we're trying to figure out for our company, what we would do is we would take a representative random sample. So you wouldn't take a whole bunch of random samples. You would take one really good representative sample. You'd make a good sampling plan to be like, okay, we need to do this, and this is how we'll sample to make sure we understand So if you're trying to figure out if orders arrive on time, you would need to make sure you look at different types of orders. So you would stratify by type of order. And then it could be a time series thing where it changes over time. So you might track it. Some companies will keep track of like where they're at. And then you can put confidence intervals on that and try to be like, okay, this is where we believe we're at right now. This is, we could be as high as this or we could be as low as this. But from our track data, this is where we're at. So companies will do that. They'll track their data and be like, here's where we believe we're at this current moment, because it does change over time. So generally, you just keep updating it. Like super unbiased, make sure everyone is... Exactly. Make sure everyone's representative. Everyone has an equal and likelihood chance of being representative, which is a really hard task. Very, very hard task. And so this interval right here, it's not about the days, it's about the parameter. I think it does it. Yeah, great job, Charlie, right there. Excellent work. 98% confidence interval. 98%. 2.3263 z-score for it. So vitamin D deficiency. Let's drop this in. Keep asking questions. Excellent work, Charlie. Charlie, 1,000 points. Keep it up. Vitamin D, whether ingested as a dietary supplement or produced naturally when sunlight falls upon the skin, is essential for strong, healthy bones. The bone disease rickets was eliminated during the 1950s, but now there's a concern that generation of children more likely to watch TV or play video games than spend time outdoors is at increased risk. A recent study of 3,200 children randomly selected. I've heard you can make good money doing inferential stats. Yeah, I bet so. A lot of people don't know how to do statistics, and it's amazing to me. I like explaining statistics to Chelsea. I'm doing the notation right here because she has a lot of really big... She doesn't want to just like repeat what I say. She wants to know the topics really, really well. So she'll go in, she'll like tell people about stuff. And they're like, how do you know all this? And she'll like, oh, my fiance does statistics. So it makes me feel proud because then she gets to be all smart. And a lot of people in many fields are decent with statistics, but understanding what technique to use and when, it's like a carpenter or something like that. Statistics is a skill set where you have to know what tool to use. And in this one, we're going to build a 98% confidence interval. So from my knowledge, I know the 98% confidence interval is 2.32, oh my gosh, 3263, right? We're going to find out the hard way here. So this is the 98% confidence interval z-score, and I'm going to really check it by going over here to R. And in R, I can do Q norm and do 0.01 and 2.326, and then it rounds up. But let me change the digits. Options, it's not office hours if Brian doesn't pull up. Good, it is 2.3263. Yeah, I know. I think stats is the most useful. I mean, you're talking to a stats teacher. So I think stats is the most useful and most applied. And if you're doing that right there, you can get this answer with the David M. Lane applet. I'll drop it in the chat again. But if you're trying to get that answer, which I have on the screen, it can be obtained via the David M. Lane applet. I like using software right here because I can get a more exact answer, and also I've got it in my head. And every once in a while, I check it to make sure I've not transposed the digit. Because sometimes I'll be like, wait, 2.3263. And there's other ones like 2.5758. That's the next one up for 99%, 2.5758. Yep. So these are different z-scores right here, and I was just carrying out more digits than one would really reasonably need to make sure we can see them all. But these are what I'm trying to get right here with this applet, where we're showing what a 98%... Oh, yeah, election. Oh, my gosh. I wish we could do, like... It's too political. I talk about it, and obviously I never want to give support for a candidate. That's not my goal. But, well, that's the thing. See, I'll show this right here. You'll see what they're building, and I kind of have my issues with it. Not because it doesn't tell you the full picture. I'll explain why I don't think this tells you the full picture. So here's the issue as we talk about confidence intervals, because this right here, what % confidence intervals are they building? Do you see it? What % confidence intervals is 538 building? What % confidence intervals is 538 building? Which tells you a lot about what's going on with especially results. What % confidence intervals are they building? And these are just proportion intervals. It's 2 proportion if we go to like right here, the popular vote. I agree. That's why it's just, these are just polls right here. This is no opinion, but like what % confidence intervals are they building? And that's what I try to do. I always encourage everyone to vote. Friends, family, students, anyone, go vote. And so I see something I don't like with this. 80%, yep. 80% confidence intervals. 80%. So what happens if they brought it to a 95%? Do you want to know how much wider their intervals would be? Well, we can do the calculation for them. To do the calculation for them, let me go and bring up David M. Lane here too. So to do the calculation for them, which we can do this, we can get this. Let's look at the z-score for an 80% confidence interval is 1.2818. And so if we go here and do 80% confidence, the z-score is 1.2818. If we go to 95% confidence, it'd be 1.96. So in terms of how much wider their interval would be, we'd go to 1.96 divided by 1.2816, and their interval would be 52% wider. Time to code the z-score for... Yeah, exactly. The z-score is 1.28. And so think about this. Mathematically, I want everyone to realize this, and that's why there's more uncertainty in all of this than we talk about. What we're talking about is p hat plus or minus 1.96, and you can just put standard error right here. Don't act weird, computer. Don't do that. And then p hat, sure, plus or minus 1.28 and times the standard error. Standard error is equal to the square root of p hat q hat over n. So this interval right here, this top interval, is 50% wider, 52% wider. So when you look at what's on these screens right here, if we were to do the classic 95%, which is kind of what everyone does, everyone usually does 95% confidence intervals. Well, yeah, I don't know if we have all their stats because I think they're doing simulations. And it just shocks me that if you look at this, these intervals would be 50% wider. So if you look at, I wish it gave the lower bound and the upper bound, you can kind of guesstimate where they're at. So the lower bound looks to be here 51, and the margin of error looks to be 2.4. So 50% wider would be another 1.5%. So when you think about it, the interval would go to about down here to be 50% wider. And then Trump's interval would go up to about here. And that's only a 95% confidence interval. There is a 98% confidence interval. There's a 99% confidence interval. But if you think these intervals are just going to get wider if you put more confidence in the intervals. So, there's already overlapping variation here in Electoral College, which is how the election's called. But these intervals would be even wider due to a 95% confidence interval being used instead of the 80% confidence interval they're using. I just think they don't want to visually show a 95% confidence interval because their intervals are going to go more like, and people are going to be like, whoa, that's a lot of uncertainty. There's a lot of uncertainty. If I could ask one question to Nate Silver, which I think I know the answer to, Nate Silver is 538, I'd say, how can you simulate these? Do simulation samples. So how do you simulate them is via done. We can do simulations. They're actually showing their simulations up here. And so these are the Electoral College votes done via a simulation right here. And yep, in our simulations at Disney Plus, thanks for that. When you do a simulation, you basically would create what would happen by random chance. So if we were to simulate a state, let's say right now, so here's, yeah, exactly. That's exactly it. There's less uncertainty because this is what we call time series. And when you go further out in a forecast, there's more uncertainty. So if they're predicting, 10 days in the future or 1 day in the future, there's more uncertainty 10 days in the future. Yeah, it's good stats. They do good stats other than that 80% confidence interval. What if we were to say, imagine this, Charlie. We were to say, let's pick a state. Let's say we have SpongeBob versus what's Patrick. I can't believe I almost forgot Patrick's name. So in this state, we have voters. And the voters are people who are either voting. So we're going to rep here SpongeBob. And they're going to vote for SpongeBob. There's 2,000 people who are going to vote for SpongeBob. And then also this is the truth. Patrick. Okay. So in this state, there's 2,000 people who vote for SpongeBob, and there's 1,900 people who vote for Patrick. Does this make sense what I've constructed right here? there's 3,900 people in the state, and the truth is that 2,000 of them will vote for SpongeBob, and 1,900 of them will vote for Patrick. Does that make sense? Does that make perfect sense right here? Hopefully that makes sense. You go out and you sample. Actually, you know what we should do? We'll do this. That's easier numbers to work with. So you go out and you sample how many voters? How many voters do you sample? How many voters do you sample, Charlie, from this voter block? How many voters do you talk to and ask them who they're going to vote for? So you're going to sample the voters, and you're going to sample how many of them. So this would be P. Yep, this would be P right here. So right now, P, this is the truth. P is that. P is that right there. That is P. So the true proportion of people who will vote for SpongeBob is 52.5%. That is the true proportion of people who vote for SpongeBob. That is the actual amount of people who are going to vote. And somehow we know it. We're just pretending we know it because it makes it easier to see what's happening if we can see the truth. In truth, you wouldn't actually know this about the world. You'd go out and you'd take a sample and the estimate. So Charlie's going to take 200 voters. There's your 200 voters. Does that make sense? These are, when you talk to people, these are the responses. A lot of Patricks in there. Man, I wish I had saved that one. A lot of Patricks. Maybe there's more SpongeBobs there. But these are 200 random voters who you're talking about. So let's call this random sample. Does that make perfect sense right here? Does that make good sense right there? We have a random sample. So now let's see, from your random sample, let's make a table of it. We assume the results are already in. Oh no, we're not gonna know the results apparently. We'll pretend we know the results, but we're just gonna talk to people. So now you look at your random sample. Your random sample has 107 people voting for SpongeBob and 93 voting for Patrick. But your random sample could have turned out differently. Look at this random sample. In this random sample, you would think who's going to win. Remember, we know the truth right now. But in this random sample, who would you predict? You'd be like, well, I went out and talked to people, and 109 people said that they're voting for Patrick, and 91 said they're voting for SpongeBob. And this is, we know the truth actually in this situation, which we don't really know it, but we do know it for this example. But in this random sample right here, you would predict that Patrick would win the election. But what have we not made yet? We have not made a what? We have not made a confidence interval. And to make a confidence interval, we'd go here very easily with code, and we'd go to a proportion test. And we would put in the x, which is 91, and the n, which is 200. And here is a 95% confidence interval for the true proportion of people who will vote for SpongeBob. And you know what's really interesting about this 95% confidence interval? I want you to see what number, and I did not plan this, what number is just barely inside of this 95% confidence interval for the true proportion of people who will vote for SpongeBob. So I'd say I am 95% confident the true proportion of people who will vote for SpongeBob is contained in the interval 38.5 to 52.6. I did not plan this example. With our confidence interval we created from our sample, we think it is possible that SpongeBob could get 50% of the vote. And what do we notice is in the interval? Does this make do you notice what's in there? P is in there. Does this make sense here, Charlie? Hopefully I'm not losing you with this example, but we saw in our sample, we saw only, where's P at right here? Where's P? For some reason I can't see null proportion. I thought I told you P in this. Am I losing my mind? We can figure out what P is by ourselves. Oh, there's P. There it is. So this is the sample estimate of P. So this is P hat. Technically, I wish it said P hat right here. But this is from the sample. 45.5% of people voted for SpongeBob in our sample. That's the sample proportion. And the truth is, on election day, 52.5% of people are voting for SpongeBob. And in here, our interval is, I am 95% confident the true proportion of people who vote for SpongeBob is contained in the interval 0.385 to 0.526. So that's not improbable to think. So even in this instance, where SpongeBob is losing in the polls, like we did a poll and SpongeBob is losing in the polls, the truth is that SpongeBob wins on election day. But if I went out and took another random sample, who do you think is probably going to lead? Because we know the truth. Who do you think is probably going to lead in this random sample if I take another random sample? Taking another random sample here, since SpongeBob is the one who's winning. Oh, that one predicts a near tie. That one predicts a near tie. This one predicts SpongeBob gets 105, 109. This is just what happens with random samples and due to randomness. You'll see SpongeBob will often be the one with more votes. And what you could do, here's where you get crazy. This is the crazy example. You ready? Instead of doing this by hand manually, we could say here, sponge votes. And we could figure out how many votes SpongeBob is getting. So what I'm going to do here is I'm going to simulate 1,000 random samples. So this is now 1,000 random samples where we go out and talk to people, 200 people, 1,000 times. Why not 10,000? There we go. Here's 10,000. This is 10,000 talks of people to see if they'll vote for SpongeBob. And you know what this is going to make? Very interestingly enough, the shape of this distribution should be normal. There we go. And where's the center of that distribution around? Where do you notice the center of this distribution is, which is the most likely amount of votes to see? It's pretty easy to tell where it's at. Where do you notice the center of this distribution is when we go out and talk to people and in random samples, like out of 200 people in a random sample, what we would expect to see? It's actually really interesting because we just did the sampling distribution of the sample proportion now. And we just made it literally. And I can probably tell you what the standard error is. That's so cool. 105. Yep. And you know what that's going to be right near? I wonder if we do this, if this will do it. I won't do that. We have to do divide by 200 in there. And look where the center of that distribution is at. The center of this distribution is right where? Remember what P is? It's at 0.525. The center of this distribution is at 0.525. And if we do P times Q over N, and then square root, we found the standard error. And if we times that by 3, look at that. If you go down 3 standard errors, it's right at the end of the normal curve. So this is 3 standard errors. Hopefully I didn't lose you. So P, remember P was 2,100 divided by 4,000. So that was P right there because 2,000, this is P right here. Does that make sense, Charlie, that is P? And so Q is this. There's P times Q over N because we take a 200 sample, square root. And this is the standard error for the sampling distribution of the sample proportion. And rather than doing it mathematically, we actually simulated it. So take a look at this. Watch this. Let's go to David M. Lane. Let's put in the mean of the distribution. And let's put in, that's the wrong one. Let's put in the mean of the distribution. And let's put in the standard error. And what do you notice about this versus, maybe I can show both of them. This versus this. What do you notice about these two graphics right here? Do you see where the bottom of this is at 0.40? And then what do you notice about that? Look at the two graphics and how similar they look. I'm going to go off the screen and I think you have another question I'm going to answer. So look at this graphic here. It goes up to 0.65. And this one goes right up to about 0.65 if you saw where that's at. Yeah, since we know... because I changed the numbers, I think, Charlie. I might have done that really quickly on you. I have 2,100 people voting for SpongeBob and 1,900 voting for Patrick. So the two of these, there are 4,000 people in this population. So this is the truth for the population. And then you can see right here on the David M. Lane, the graphic we get for it is exactly what we get via simulation. And so this kind of went into a little bit on how can we simulate results. So our simulated result is exactly what the statistical theory says we should get. If you look at my simulation right here of what would happen when we take random samples versus what we see according to statistical theory for the sampling distribution of the sample proportion. And the reason we didn't do simulations in the past is because I literally created 10,000 random samples right here. And I'm using a very, very powerful computer, and people really didn't have till literally the last 20 or 30 years. I mean, you go back 20, 30 years, you're not going to really have a computer that could do this well. But I'm creating 10,000 simulated random samples of what would happen if we talked to 200 people and how many voted for SpongeBob. Yeah, it'll say we know that. You're exactly right, Charlie. It'll say we know this amount of people vote for exactly. And so this right here as a question would read, we know that 2,100 people are voting for SpongeBob out of the 4,000 people. We go out and we take a random sample of 200 people, and then we went and did it. But did this make a little more sense on the simulation? And then this is kind of how Nate Silver can do his simulations if they have estimates of reality. So if Nate Silver has estimates of reality, he can simulate states, and he could just do a bunch of simulations of like using the polls from states. He could simulate that state and say, well, there's this uncertainty because he has from the polls an estimate of what the truth is. And then he can create simulations to say, in this percent of the simulations, if the polls are true, in this percent of the simulations, this candidate wins. But you can see here there's a bunch of uncertainty. Even though SpongeBob is going to win the election, even though SpongeBob is going to win the election, there's so much uncertainty. Really? You're gonna do that? We could predict, like you could get a random sample that could have SpongeBob down here at 40%. So there's a lot of uncertainty. Your random samples could give a lot of varying results, and so that's kind of the cool thing about polls and everything is people are always like, oh, the polls got it wrong, and it's like, well, you do realize that they were saying in 2016 that Hillary would win by 3.2%, and then she won the popular vote by 2.1. But that's not how we do elections. Once again, but in regards to popular vote, the poll was pretty close. It was up by about 1.1%. Before anyone thinks this website's been up for a long time. You can look at the change history on it. But polls are pretty good. They're not perfect. There's variation in the poll. There we go. And so take a screenshot of this and bring it over. But because so many random ads on these sites, with the polls right here before the election, there was a poll predicting Trump would win. It was LA Times USC tracking said Trump would win. And so it's just a poll of individuals. And so here's the polls in 2016, and the average, that stands for Real Clear Politics average. The average for the recent polls was 3.2%, and then the overall final in the election was 2.1%. Once again, that's the popular vote, which is not how we call elections. But the polls were off by 1.1%. And some of these polls, like 1 and 3, I mean, they're super close. So, but it is a time series thing that changes over time as we get closer to the event and we can be more certain about. And these polls have margin of errors. All these votes, what's really funny, the one that predicts Trump wins is not within the margin of error. Why does that poll not have a margin of error? That is weird. I don't like that. I guess they didn't grab it, whoever entered it in the data sheet. This poll right here has the win within the margin of errors. This poll has within the margin of error. This poll has the answer within the margin of error. This poll has the answer within the margin of error. This poll is just barely outside the margin of error. This poll is also just barely outside the margin of error. And they are a little further back than Election Day, because I think Election Day was November 7th. So some of the I'd say half the polls half of the recent polls have it within the margin of error. So, and they should do a margin of error on this. So if you look how close it was, Clinton actually got more than the poll, but of course Trump did too. So there's what they expected the amount to be. And yeah, so it's really cool looking at it. How would we find P hat given P? So you wouldn't necessarily find P hat given P. P hat is going to be for the sample. So I'll write it as it is. P hat is going to be from the sample, and it's equal to the amount of successes in the sample over N, which is the number of trials, and P is the truth. So whenever we give a P, we're saying something like the true proportion of people who are going to vote for a candidate. So you'd actually have to know it. It's actually the truth. And if you have P hat, it's always going to be related to a sample, like in a sample of blank amount. So one way to know it's P hat, if you have a sample size. So if we say something like in a sample of blank, like in a sample of 200 people, 110 said they're voting for SpongeBob, then you would have right here 110 over 200. But then if this says the truth for the population is that 55% of them are going to vote for SpongeBob, then this would be for everybody. That's the truth. So you can't necessarily find P hat from P, but you can use P to make the sampling distribution. So we don't need P hat if given P. So here's a really big concept, Charlie. Like, this is big. You ready? So if you have P, you can ask what happens when you look at p hat. This is sampling distribution. If you have p hat, you can use it to estimate p. And so this is confidence interval. So if you have a sample, you can use it to estimate the truth. That's going this way. If you take a sample, like if we, before the election, we will use the sample results to estimate the truth. Does that make sense right there? Oh no, it's all right. This is a big concept. This is why I'm reviewing it this way. So if you have a sample, you can make a confidence interval to estimate what the truth would be. But if you have the truth, you could then ask what might happen in a sample. So if you know the truth, you could ask what happens in a sample. So if you know the truth, you can ask what might happen in a sample. So imagine you have a shipping company and you know from historic data that 2% of your products are broken. You know historically 2% of your products are broken. Have I just told you P or P hat? You know historically 2% of your products are broken. You know historically 2% of your products are broken. So historically 2% of your products are broken. Is that P or P hat? If you know historically, that'd be P, because that's it's the truth. We're saying we know historically that 2% of our products are defective. So since you know 2% of your products are defective, then we would go right here and we would say, okay, so what might happen in a sample of 1,000 that we send out to our customers? We're going to send out because we're a company that sends out like large scale items. So we're going to send out 1,000 products. And what would we expect in the 1,000 products? Well, we know that the distribution will be normally distributed with a mean of P and a standard deviation of P times Q over N square root. And this is what we would expect to see for the distribution of broken products. And I shouldn't put it down there. It looks like it's with the confidence interval. This one should go up here. Let me erase what I have up higher. This one should go up here because we're going to use it to estimate what happens in a sample. So right here, we're going to use normally distributed with a mean of P and a standard deviation of P times Q over N square root to ask what might happen in our sample. Now, maybe we work for a brand new company, and at the brand new company, we don't know what % of our products are broken, and we don't have data on this. So someone says, go to the line. This is a whole different question now. Someone says, go to the line. I want you to take a sample of 100 random products, and let's figure out what % of our products are broken, because we don't know. We're a brand new company. We don't have data on this. Let's try to figure out what % of our products are broken. So we're a brand new company now. We take a sample of 100. So you take a sample and use it to estimate the population exactly. So now we take a sample and we make a confidence interval to ask what might happen here. And this is where we do P hat, because we only have P hat, plus or minus Z square root of, we only have P hat, so we're using P hat right here. And this is when we take a sample. And that's P hat. So this is when we are a brand new company and we're trying to estimate. We say, okay, let's take a sample to figure out what proportion of our products are broken. So why would you want a sample if you know the true proportion? So in this example, we're going to ship our products to a very important client, and we want to know if they could possibly get more than 1% bad products. So in this example, we have to know the truth. We know that 2%, well, then we are obviously going to get more than 1%. Let's say 3%. So in this example here, we know that 2% of our products are broken, and we don't want the customer to get more than 3% defective products. Like the customer's like, I'm canceling my account if more than 3% of the products are defective. So would we think that they would get more than 3% defective products? So since we know that 2% of our products are defective, what % of the products would you expect to be defective in their shipment of 1,000? So since you know that 2% of their products are defective, what % of products would you expect to be defective in the shipment? So since you know 2% are defective at your company, you'd have to know this to say what you would expect to see. So remember, it's P right here. So since we know 2% are defective, we'd expect 2% defective. Then right here, we're going to have P times Q over N square root. And so now we're going to solve for the standard error of the distribution. And it's going to be 0.02 times 0.98 divided by, and they're getting 1,000 products. And then we square root this. Ooh, this is a little scary here. 0.0442. So this is 0.0442. And that's the variation we'd expect in the distribution. Now we go here, we draw out the distribution, and I'm going to use David M. Lane to help me out. And that's, yeah, exactly. And so it's P times Q over N square root because we know the truth. And then we're going to go here to David M. Lane, and we're going to put in our numbers that we just found. And here's where I'm a little bit worried. What do you notice is at the upper end of this interval? And so what do you notice is slightly possible, but kind of improbable? Because we could figure out the z-score of this by dividing 0.1 by the standard error, or standard deviation, excuse me. We could divide 0.1 divided by that and get the z-score. Oh, it's 0.01. There we go. Oh my gosh. There we go. It's 2.25 is where the z-score would be at. And so what do you notice? That 3 is a little more than 2 standard deviations away, so I'd be a little bit hesitant. I'd say there is the possibility you could get 3 defective or 3% defective products. It seems unlikely, but in this shipment of 1,000, it's not out of the bounds of reasonable possibility that you could see 3% defective product. Do you think the customer would see 4% defective product? Do you think it's possible the customer could see 4% defective product? In our shipment of 1,000 products, do you think it's possible the customer could see 4%? Yeah, and so we're saying we know from our data, like some companies might know this, that they might know 2%. Like imagine if you work at Coca-Cola. Yeah, the 4% is like very unlikely. That's a z-score of, it can't be right. Oh, because it'd be 4 minus 0.02 because it's what we observed. There we go. And so the 4% is a z-score of 4.5. It's 4.5 standard deviations. It'd be up here somewhere. So this would be even more unlikely. We'd say there's really no way you should get 4% defective products. It's possible you probably are going to get between 1 to 3%. Yeah, exactly. It's possible to get 0% defective products, but that's very unlikely also. You're probably going to have some defective products, probably about 1.1% to 2.9%. If you notice, that's about within 95% of observations. So probably I'd say to them, it's not, I would probably say that. I'd say it's not unlikely for you to see around 1 to 3% of our products defective. We know 2% of our products are defective, and it's not unlikely for you to see around 1 to 3% of our products being defective in a shipment of 1,000. So I'm telling them what they expect to see in a what of our products. So I'm using what I know about the population to tell them what they might see in a what. So I'm using what I know about the population to say, well, from a this, you would expect to see this. I'm using my knowledge of the population to talk about a what? A sample, yep. So I'm using my knowledge of the population to tell them what they might see in a sample. But if you go this way and you only have a sample, you could say, well, let's go out and poll people and ask them who's going to win the election. At this point, you don't know the truth of who's going to win the election. So now you're trying to estimate who's going to win the election. Does that make sense why we go this way here? If you're saying, okay, it's before the election, let's take a poll to figure out what the truth for the election might be. Yeah, for especially like supply chain or stuff like that, like if you're trying to figure out, if we know this about the population, then what would we expect to see in a sample? Like, especially with times, like how long something might take to deliver something. Yeah, and then you can figure out the truth about the population too. It just depends which way you want to go. If you want to use the truth to figure out what you might see in a sample, or use a sample. So you have to know the truth is the problem with the other way. If you go the other way, you actually have to know the truth. You have to know the truth to figure out what you might see in a sample, which someone might say, do you really know the truth? Or do you have to have an estimate of the truth? Has this helped make a little more sense differentiating these two concepts? Is one more confident than the other or no? It's just kind of two different techniques. It's like a knife and a fork. You wouldn't really use one for the other. If I was like, pick this up with your knife, you'd be like, can I use the fork? Or like, cut this with your fork. You'd be like, can I use the knife? You'd be like, I can try to. It just wouldn't be right. Wouldn't be right. One uses the truth to estimate what you might see in a sample. The other uses a sample to estimate what the truth is. If you know the truth, you'll probably be estimating for samples because you wouldn't estimate the truth if you knew it. Does that make sense too? If you know the truth, you wouldn't estimate it. And if you know the truth, you can then use it to say, what might I see in a sample? And then you can, like with shipments and supply chain, it might really help. Because then you can talk about the expected variation. You can say, we know, like if you're talking about like how long it takes for something to arrive, you could say, we know from historic data that we see it takes this long for things to arrive, but we also know that there's this variation in how long it takes. So if you have this many packages, it could take about this long for them to arrive. And so that can help with supply chain a lot. Like it just depends on when you need to use stuff. I do think conference roles are more important. I use conference roles more often too. So I do agree 100% with you, Charlie. Really great questions. I hope this helped differentiate these two topics. Kind of a good drawing. I might try to use this, make it look pretty, and I might do a video with it this weekend, talk about the difference between these two. But that's got it. I'm going to go teach some 320, answer some emails. I'll be back. Talk to everyone later. Bye, Charlie. Great work. Great questions. Excellent stuff. Keep asking the big questions. You're doing excellent. Talk to you later. Bye.